This is the first lecture of Chapter 15, which deals with quite a few new concepts. One is chirality. So we'll define that term and that concept. And one definition is the handedness of molecules. So let's see what this chapter is all about. So in this presentation, we will cover the following. A definition of isomers, which we have covered before in Gen Chem. We'll also look at stereoisomers and see if we can determine the difference between isomers and stereoisomers. Next, we'll look at the analysis of isomers in 3D space or three-dimensional space. We'll introduce a new term called chirality. And lastly, we will apply the concept of chirality to different molecules. So I know this sounds very strange because it is such a new topic, but we'll take it slowly so we can understand it. One thing that I would really and highly recommend is a model set. So if you can purchase one or borrow one, it will be extremely helpful to visualize these molecules and understand the concepts that we're going through. So I really recommend doing that. Let us begin. Isomers are molecules with the same chemical formula, same number of carbons and hydrogens and heteroatoms. Key, but there are different arrangements of the atoms within the molecules. Different arrangements. Here are two examples. The top here are called constitutional or structural isomers. Notice here we have C4H10O. So one representation of this is 2-butanol. So notice this carbon here has an OH, a methyl group here, a ethyl group, and of course a hydrogen that's here, that's typically not drawn in the line angle. 1-butanol has the same molecular formula, but the atoms are arranged differently. So the same carbon here, as we have seen here, it does not have the OH group. This carbon, however, has the OH group, and this carbon in that 2-butanol does not. So these are called constitutional isomers. Another term is structural isomers, where the atoms are arranged differently in terms of being on different bonding arrangement. Another type isomer is the geometric isomer. So let's look at this molecule, C2H2Cl2. One isomer is this one. Notice this carbon here is bonded to a hydrogen and a chlorine. This carbon here is also bonded to a chlorine and a hydrogen. Over here, this carbon is the same as this carbon, and it's bonded to a chlorine and a hydrogen. So in other words, now the bonding arrangements are the same. Notice the key here is bonding arrangement are the same. However, the arrangement in space for these atoms are different. Keyword here, arrangement in space. I'll even go further to say the arrangement in three-dimensional space. So here the chlorine atoms are across this double bond plane, and that's why it's called the trans isomer. In this isomer, the two chlorine atoms are on the same side of the double bond, and it's called a cis isomer. So these are known as geometric isomers, and these are called constitutional isomers. The difference here, again, let me emphasize, for the geometric isomer is that the bond connectivity are the same except the arrangement in 3D space. A term that we'll use for this is stereoisomers. Stereo here means arrangement in space or spatial. So the difference here is that geometric isomers are also known as stereoisomers because the groups are arranged differently in three-dimensional space, but the bonding are the same. So let's see if we can summarize this. So we have isomers. And of course, as we have described in the previous slide, we have two types of isomers. One is the constitutional isomers, and the other is the stereoisomers, where they are arranged differently in space, or the orientation in space are different. Stereoisomers can be further classified as cis and trans isomers. And what we'll do in this lecture is that there is another type of isomers that are stereoisomers, and they are defined as enantiomers and diastereomers. But in this lecture, we'll concentrate on enantiomers. So that's a new term for us, enantiomers. So we'll define that and understand it and be able to apply that. Okay? All right, so let's begin. So below are two amino acids. We're all familiar with amino acids. They are the building blocks of peptides and proteins. These particular amino acids are alanine. And I'm sure we are familiar with L amino acid and D amino acid. So we have L-alanine and D-alanine. They are both the same amino acid in terms of molecular formulas. So the question now is, are they the same or are they different? We know from biology that the L and the D amino acids are different based on its usage in protein synthesis. And only one of these, L and D, only one is used in protein synthesis. So the bottom line here is the body can recognize one and not the other, which is implying that they are different. But let's see how different they are. Here is a schematics of the interaction of molecules with an active site. So we have a binding site here, which we label as B, C, and D. And here's a molecule, an atom here, that has 4 groups bonded to it, A, B, C, and D. For activity, they must fit perfectly into these sites. So this one will have biological activity. If the molecule here, if the bonding arrangement in space or the spatial arrangement are different for the same A, B, and C, and it cannot fit into the active sites, there is no activity here. So that's just an illustration of the body recognizing specific orientations of atoms in a molecule in space. Here's another example. And here is an atom, carbon, which has 4 different groups bonded to it. Here's C2H5, CH2OH, and here's an hydrogen, and here's another group. And it must fit perfectly into these active sites for activity. If it does not, even if one does not fit, it does not work and there's no activity. So conclusion, the body can recognize molecules in terms of the spatial arrangement of the atoms in those molecules. So they may be different, or they are different. So let us start our lecture of differences in spatial arrangements of atoms. So let's start our lecture by looking at our hands. So here is a copy of the left hand and the right hand. So the question now is, are they the same or are they different? Very profound question, because we look at our hands every day and we tend to just conclude that they are the same because it has both hands have 5 fingers. So they look to be the same. But if you do a careful analysis, they are not the same. One test that can be done is, in the winter time, if you put your left hand glove on the right hand, it does not fit. And if you put the right hand glove on the left hand, or vice versa, it does not fit. So therefore it implies that the left hand is different from your right hand. So start using that as a starting point. Let's see how we can determine if 2 molecules are the same or are they different, even though they look pretty much alike. So let's start by looking at these 2 molecules here. So here is a carbon atom, and it has 4 different groups bonded to it. I'm emphasizing 4 different groups because you'll see that will become very important in our analysis. So this carbon atom here has a yellow, a white, a green, and a red atom or atoms bonded to this carbon atom. This other molecule has the same yellow, white, green, and red atoms bonded to this carbon. So the question is, are they the same or are they different? It's very difficult to look at these 2 molecules and come up with an answer. So let us introduce here a criterion to determine if these 2 molecules are the same or different. Once we have understood this criterion, we can apply it to different molecules. So let's look at this. The criterion for determining if they are the same or different is if they are superimposable, which means that if you physically take up these 2 molecules, that's why I'm recommending using your model set. If you should physically take up these 2 molecules and orient them so that there is complete overlap, green and green, red and red, yellow on yellow, and white on white, they are superimposable. If they are superimposable, they are the same molecule. So you can see what we'll be discussing in this chapter. It requires visual understanding of molecules in 3 dimensions. So it's going to take you quite a while to visualize these molecules in 3D. And that's why I'm recommending again getting a model set here, because we are communicating here in 2D. We're only seeing things on the screen, 2D. But there's really another dimension, which is the depth of this spatial arrangement. So conclusion, if you have 2 molecules, and if they are superimposable, completely superimposable, they are the same. Okay? So, let's extend that concept now into real molecules here. So looking at this molecule, here's a carbon, and it has 4 different groups bonded to it. A methyl, an ethyl, a hydrogen, and an OH, hydroxyl group. Same here, carbon, an OH, a ethyl, a methyl, and a hydrogen. The question is, are these 2 molecules the same or are they different? Of course, what this involves is, can you visually look at these 2 molecules and orient them to determine if they are superimposable or not? This is a very challenging task. So you can see here, you will have to really build your 3D perception of analysis. So, but let's see if we can find a way of doing it a little easier. So let's look at this. So, conclusion of the previous slide is that if you can visualize it, these 2 molecules here are really superimposable on itself or on themselves. So therefore they are the same. So these 2 molecules here, if you can build it by putting 4 different groups on and label them as ethyl, methyl, hydrogen, and OH, and another molecule as ethyl, methyl, hydrogen, and OH, and see if you can superimpose them, they are the same. So in this case, they are the same. If you're really good at analysis in 3D, you can just visualize these 2 molecules and put the OH over here. You can see that the H will superimpose over here, and the methyl over here, and the CH2 here. So they will superimpose, so therefore they are the same. Okay? So once again, let's not panic here in terms of this is a real tough concept. It's not if you have a model, but we'll find an easier way to determine if these 2 molecules are the same or different. Let us look at and do another analysis here. This time we have the carbon with the same white, green, red, and yellow, and I've built here another molecule with the same green, red, white, and yellow. So I can ask the same question here. Are they the same or are they different? You may say, well, gee, it's the same because it's just what you had in the previous slide. But let us do the application. Are they superimposable on each other? So what I did here is I took them and I tried to superimpose them. And what you can see is that the white and the white will overlap. The red and the red will overlap, but not the yellow and green. So there's no overlap here and there's no overlap here. So therefore these molecules are not superimposable. So therefore they are not the same. They are stereoisomers of each other. But as you may recall, we have different type stereoisomers, cis and trans. These are not cis and trans because there's no plane for these groups to be across. So we have to introduce here a new term for stereoisomers of this type. So let's see what that term is. Non-superimposable stereoisomers are called enantiomers. So that's a new term for us, enantiomers. Here's another aspect of enantiomers. If we have the same molecule, carbon with yellow, white, red, and green, and assume this is a mirror right here. The mirror image of this is here. So the mirror image of this molecule here is its enantiomer, or it's different. To bring it back to the example I had earlier, the mirror image of your left hand is your right hand. So therefore, your left hand is different from your right hand. Of course, as we emphasize, because the left glove does not fit the right hand. So they are different. And your left hand is the mirror image of your right hand. Same concept here. Here's a molecule. The mirror image of this molecule is right here. So imagine this is the mirror. The red reflects here, the white here, the yellow here, and in the back we have the green. So they are mirror images of each other. Conclusion, they are non-superimposable, and the term that we have here is they are different molecules, and they are enantiomers. Another way of looking at it, they are stereoisomers that are specifically defined as enantiomers. So that's a new term. So let us summarize to an extent. So enantiomers are non-superimposable mirror images of molecules. Keywords: non-superimposable and a mirror image. Here's an example. Here is a carbon that has 4 different groups bonded to it: a methyl, a ethyl, a OH, and a hydrogen. Here's the mirror. So the mirror image here is this molecule. So this molecule here is different. Let me circle it. This molecule is different from that molecule. So in summary, this molecule has a carbon that has 4 different groups bonded to it. Right? 4 different groups. That's going to be key in determining if a molecule is possible to exhibit enantiomerism. Again, so this molecule here, its mirror image is non-superimposable, and the term that's used is they are enantiomers. Don't forget that term. Enantiomers are non-superimposable mirror images of molecules. So let's get back to amino acids. So this again is the same we had before. So here's the L amino acid, and here's the D amino acid. So here we have a carbon of that amino acid that has 4 different groups bonded to it. So it's possible to have, for the mirror image to be different. So what we need to do is to look at this and determine if they are the same or are they different. Notice this is using the line, not the line angle, but also the dashed wedge. Formula, where the wedge would be in front and and the dash would be in the back. So notice here, the wedge has a methyl group in this molecule, and over here the wedge has a hydrogen. Different. The back, or the dash, has a hydrogen here and a methyl group here. So again, that's a way of illustrating to us, making it easier, that these two molecules are different because the orientation in space of the atoms bonded to this carbon that has 4 different groups around it are different. So therefore, these two molecules are in fact not the same. They are stereoisomers, and specifically they are enantiomers. Here's another term. They're called chiral molecules. We'll define that on the next slide. So chiral molecules, well, I can tell you now, chiral molecules are molecules in which there is a carbon that has 4 groups around it, and it's possible for its mirror image to be different. So let's look at examples of chiral molecules. So here's the definition. So chiral molecules, also known as stereogenic molecules, have at least one carbon that has 4 different groups bonded to that carbon. So let's look at this. Here's a carbon. It has a ethyl group right here. It has a propyl group here, and it has a hydrogen that's not shown. So it has 4 different groups. The term that's used to describe this carbon that has 4 different groups is a stereogenic carbon. If you break down the word, you will see that stereo means orientation in space, and of course stereogenic means the orientation of this particular carbon, the groups that are oriented in space that are bonded to this carbon. So this carbon is known as a stereogenic carbon because it has 4 different groups bonded to that carbon. This molecule, its mirror image will be different from this molecule. So therefore its mirror image will be its enantiomer. Let's look at the next slide and see. So let's apply that concept. Same molecule, ethyl group here, propyl group here, hydrogen, and OH group. The question now is, are they the same or are they different? Notice again that the bonding arrangements are the same. This carbon here has a hydrogen, a OH, a propyl, and an ethyl. The same carbon has an OH, a hydrogen, an ethyl, and a propyl. Same carbon. So the bonding is the same. What's different, however, is the arrangement of the group in space, as shown here by the dashed and wedge. So again, I'm just emphasizing, it's best if you can build this using your model set and putting this group in front and this in the back, and building it again using a different molecule, and put the H in front and the OH in the back, and see if they are the same. See if they are superimposable or not. What you will discover is that they are not superimposable. They're non-superimposable, which would imply that they are enantiomers. So let's look at this. Here's another example. This one here is, this carbon has now 3 different groups, not 4, because we have here the propyl, CH2, CH2, CH3, and the same propyl over here. So these 2 groups here are in fact the same. And of course there is a hydrogen bonded here. So it has only 3 different groups that are bonded to this carbon. So therefore this carbon is not stereogenic. So we say it's non-stereogenic because we have defined the stereogenic carbon as one that has 4 different groups. So if it has just 3, it's non-stereogenic. Here's the key. If it has 3 different groups bonded to this carbon, its mirror image will be the same. So therefore it is not the enantiomer. So let's look at this. So now we have drawn it. So here is the same molecule. This carbon here has an H, an OH, a propyl, and a propyl. The same carbon has a propyl, an H, and an OH. Bottom line is this is in the back in this molecule. The hydrogen is in the back, whereas now it's in the front. The OH is in front for this molecule, and the OH is now in the back. But the bottom line is that because these groups here are the same, it's non-stereogenic, so therefore the mirror image of these 2 molecules are superimposable on itself. So you can see here that there is a little easier way to determine if 2 molecules are the same or are they different. Key is to look and find a carbon that has 4 different groups bonded to it. If it has 4 different groups bonded to it, it's possible to have its mirror image will be different. If that carbon does not have 4 different groups like this, its mirror image will be the same and hence superimposable. Okay, so summary. So objects that are non-superimposable on their mirror image are chiral. Notice, not superimposable. And of course, now you can see the connection. This is a Greek word. It comes from this word here, chiral. So therefore, which means hand. So that's why it's the handedness of this, because the left hand and the right hand are different. So once again, a molecule that's chiral has 4 different groups bonded to a carbon. Its mirror image is non-superimposable on its mirror image, and therefore it's a enantiomer. Okay, let's go through these. I'll cover these. And there's a stereogenic center in a chiral molecule. Remember here, stereogenic center means that there are 4 different. The key here has to be different groups bonded to a carbon. So that's important. 4 different groups bonded to a carbon is called a stereogenic center. If you have that, that means that the mirror image of that molecule will be non-superimposable on itself, and therefore the relationship is enantiomers. The stereoisomers are called enantiomers. As we've seen here, they're called enantiomers. So these are some new terms for us, so that you really have to take time to understand the concept of these terms and also be able to apply the concept of these terms. So let us start applying this. So here is a practical application of the concept of enantiomers. Here's a molecule that we're very familiar with, ibuprofen. It's an over-the-counter drug, as you've seen here, and it's used as a painkiller. Of course, as we all know, have a headache, you take a couple ibuprofen. But here it is. A close examination of this molecule shows that there's only one carbon here that has 4 different groups bonded to that carbon. Okay, notice here, just to emphasis, this carbon here does not have 4 different groups bonded to it, because here is a methyl group and here's a methyl group. So that's not a chiral or a stereogenic center. Here is the stereogenic center. So therefore its mirror image, if you were to put a mirror right here, its mirror image is here. So this molecule here is different from this molecule here. So whenever you buy ibuprofen, you really are buying 2 molecules of ibuprofen, and they are different. One is inactive and the other one is the active enantiomer. That's the painkiller. So what's done in the pharmaceutical industry, they try to get as much of the enantiomer in that tablet as possible so that it's more effective. As you can imagine, if you bought ibuprofen and it only had this enantiomer in it, it would not relieve your headache. But this is the one that does the job. So these 2 molecules are in fact different. Let's reintroduce some terms. They are enantiomers. The mirror images of these 2 molecules are different. Here is a stereogenic center. Why is it stereogenic? Because it has 4 different groups. Here's 1, here's 2, here's 3, and all of this is the 4th group bonded to this carbon. So that's a practical application of enantiomers. In summary, so objects that are non-superimposable mirror images are chiral. Most chiral molecules exist in organic chemistry. As far as we're concerned, all have a carbon that have 4 different groups bonded to that carbon. That's the stereogenic center. Stereogenic center with 4 different groups. Objects that are superimposable, notice here superimposable, are achiral. Achiral, which means that they are superimposable on its mirror image. So non-superimposable mirror images of each other are called enantiomers. And of course, as we have seen, enantiomers always come in pairs because they are mirror images of each other, just like your right hand and your left hand. And this is the end of that first lecture for this chapter. So once again, I know this chapter is very involved because it brings in a lot of new concepts, and we have to understand these concepts and be able to apply these concepts by looking at different molecules to determine if they are enantiomers or not. So take your time going through this video presentation. I'll also post the PowerPoints. So read along in your textbook and make sure you understand the concepts. So remember once again that we're here as students of organic chemistry, not only to learn the facts and the contents and the definitions of these terms, but we are also here to think and apply this understanding to solving problems. So that's what we do as scientists. So continue to work hard, and I'll post this on the PowerPoints, and just keep working.